Hi, folks. I have the privilege of having Brian Kernighan here with me today. How are you doing, Brian?
Marcelo, I'm doing fine. It's a pleasure to talk to you.
And thank you so much for joining me. You work at Princeton today, right? So you teach a course named Computers in Our World. And I'm just wondering if you could tell us a little bit about the work at Princeton.
Sure. So I've been at Princeton a little over 20 years now. And for a lot of that time, I have been teaching every fall a course that, as you say, is called Computers in Our World. It's basically a course about computing and communications for people who are very, very non-technical. A typical person in the class is a history major, maybe an English major, maybe a music major, something like that. And so what I'm trying to do is to tell them about technology that is already having a tremendous effect on their lives and is likely to continue to do so in the future. So the hope is that by the end of the course, they will understand a lot more about the things that go on in the world around them that are technical, because so much of that is based on computing.
Going back in time, and I know you're going to tell me in a few minutes, but how did programming come into your life? I realized that programming back then was very different than today, but I was just wondering, how did programming come into your life?
Well, back in in those days, there were dinosaurs still walking the earth, and so it was a very different kind of computing environment. I actually didn't encounter my first computer until I think I was probably at the end of my third year in university, somewhere in around that. And I saw a bit of computing at the university, and I had a summer job that had there was a computer nearby, although I didn't actually use it. And so I think it wasn't until my last year as an undergraduate at the University of Toronto that I actually used a computer for anything. And even that was fairly superficial. But then I had internships and I did graduate work at Princeton. And so I did more computing at that point. And so it slowly crept into my life, but not very early compared to most people these days.
Going a little bit back further in time, can you tell us a little bit about your high school experience and what led you to your bachelor degree in engineering physics at the University of Toronto?
Sure. So I grew up in Southern Ontario, basically in Toronto, and then we moved when I was about 15 to a very small town outside of Toronto, maybe 50, 60 kilometers west of Toronto. And so it was a very, very small high school, very, very small class. And so there wasn't much there that had anything to do with other than just the basics of education. But my father was a chemical engineer. He ran a very small chemical company, and he had been a chemical engineering major at the University of Toronto. And so it seemed like sort of the natural thing for me to do to go to the University of Toronto. But I didn't have any real interest in chemistry. I was probably more interested in electronics. And so I wasn't sure what to do. And I had a high school math teacher who suggested that I take the course that you mentioned called engineering physics. And what that was basically a lot of engineering, but also a lot of math and physics and chemistry for kids who were interested in engineering, or at least thought they were, but didn't know what kind. And so it was a fairly very challenging course. It was the kind of thing that in other schools might have been called a weed out course. That is, to weed out the people for whom it wasn't the right choice. And it was 4 years of very hard work, but I did get a pretty solid background in a lot of different things, both the call it the more theoretical and lots of math courses that were useful in physics and chemistry, but also some practical engineering sorts of things. Because there was, for example, a component about civil engineering. And so we learned about concrete and reinforced beams and so on. So it was a very tough course, but it was kind of satisfying in a way. And I don't think I've ever worked that hard in my life since just to get through that.
I was hoping you could tell us a little bit about your PhD as well. I think you did a PhD in electrical engineering from Princeton in 1969, correct?
Yes, that's right. So after I graduated from Toronto in 1964 in this course called engineering physics, which is now called engineering science. They changed the name just after I graduated. And I went to Princeton. I had applied to a number of universities, mostly in the United States. It wasn't all that common for Canadians to go to the United States for graduate school. It was much more typical for people to simply go straight to work, or if they were going to go to grad school, to stay in Canada. But I went to Princeton in part because I had a good friend who had been a year ahead of me at Toronto and had then gone to Princeton as well. This is Alejo, who shared the Turing Award last year. So very, very distinguished guy. But I went to Princeton, and there was no computer science department at Point. There was a small collection of very young faculty in the electrical engineering department who were interested in computing. And computing at that point was a very, very young field, much too early to have separate departments, and not really quite clear what the topics of a computer science degree ought to be. But it was a good group of people. Princeton was a great place to be. And so I spent 4.5 years at Princeton getting my PhD, and graduated very early in 1969.
How did you get to Bell Labs? I think you're an intern at Bell Labs at some point in time, correct?
Yeah, what happened there is at the end, I think, of my second full year at Princeton, I got an internship at MIT, and I was working in the group that had developed CTSS, the compatible time-sharing system, which is a very, very nice computing environment, and one of probably the first like it. And that group had just embarked on the Multics project, which was an attempt to do all of the things in CTSS, but do them better, bigger, faster, more complicated, more of everything. And I got that internship at MIT, I think through good luck, but also because a Princeton grad student had been there the summer before, had done a good job, and they probably thought Princeton people would work out okay. So I spent a summer there in what was called Project Mac and working on tools for this new Multics operating system. And as part of that, I sort of knew of work at Bell Labs, which was going on because Multics was a joint project between MIT and General Electric, which made hardware, computers at that time, and Bell Labs, which was a real software operation. And I think that gave me some contact. And in the following summer, this would be the summer of 1967, I got, again, through probably just good fortune of knowing people, an internship at Bell Labs in the research department in Murray Hill, New Jersey, which is sort of, I'll call it 40 kilometers southwest of New York. So I spent that summer there. I worked with Doug McElroy, and I had such a good time that when they offered me a chance to come back the next summer, that is the summer of 1968, I came back again. And at that point, I actually had to get serious about a thesis. So I worked with Shen Lin on a combinatorial optimization problem that my thesis advisor had suggested, and Shen and I came up with heuristic techniques for solving it. The problem was called graph partitioning. Take a graph, that is the kind of graph that has nodes and edges, and you try and divide the nodes into two equal sized piles such that the number of edges that goes from one side to the other side is as small as possible. It's called graph partitioning because you're partitioning the graph into two equal sized pieces. And we never did figure out an efficient way to solve this problem, but Shen and I came up with a heuristic that did a decent job on it. And I came up with a couple of special cases where you could actually do an efficient computation. And that turned into a thesis. It turned out that, of course, at about the same time, other people were doing theoretical work on why is it that some problems seem to be so hard? And this was the work of, in particular, Stephen Cook, on the idea of NP completeness, problems that were easy to prove that you had the right answer, but not easy to solve. And it turns out the graph partitioning is a fine example of an NP complete problem. And so that's the reason that we never came up with a technique that was guaranteed to be efficient. So long story short, I did actually finish my thesis and went to Bell Labs as a permanent employee right at the beginning of 1969.
Brian, I was hoping you could give a brief overview to our audience of how computers and computing in general looked like back then, And you also mentioned Multics, and I was wondering if you could speak a little bit more about Multics and explain the importance of Multics in the evolution of operating systems.
Yes, well, again, back to the dinosaur comment. When I started computing, there were only a very small number of computers in existence, period. They tended to be very large computers physically. That is, at the University of Toronto, there was one big computer called an IBM 7094, I guess. And it served the entire university community. It may have been the only big computer in the whole country. And so that meant that you had to use it by writing a program on punch cards, which were basically pieces of paper with holes in them representing information. And so you would take a few hundred or a few thousand of these cards, which had a program and its data, and you would hand it to an operator who would hand it to the computer. And sometime later, you might get your results on printed pieces of paper. And if you made a mistake, you had to repeat the whole process. And so it was very slow. You might be lucky to get a run of your program every hour or two. It might even take a day before you got results. And so that part of the world was very different compared to what we see today, where you interactively type a program into a computer and say compile it, and a few seconds later it's done. The thing that I mentioned CTSS, the compatible time sharing system, and what that was, it used basically the same computer actually, an IBM 7094. But what it did was to share the computing resources of that computer with a number of users, perhaps 20 or 30. And it simply switched its attention very quickly from one user to the next to the next. And of course, most users weren't doing anything. They were sitting there thinking. And so it gave each user the illusion that they had the whole computer to themselves by doing this time sharing idea. And it was incredibly more productive and incredibly nicer than punch cards. Programs were stored on a disk on the computer, and results were printed on your own terminal. That is a device like an electric typewriter that printed on paper. And so in that sense, the world was very different. So CTSS was a very productive, very nice environment. It's hard to describe just how nice it was for the time. And so what Multics was, and that's Multics, what Multics was an attempt to take the good ideas in CTSS and scale them up. It was meant to be an information utility. That is something where people could just use computing from wherever they were, and there would be a central computer that would provide the service. Both of these things sound, of course, very much like cloud computing today. And I suppose arguably that's what they were. So Multics was a joint project between, as I mentioned, MIT, General Electric, and Bell Labs. It was physically mostly at MIT because they had done CTSS. They had that expertise and that computer system very easily available. But other people from Bell Labs could use it remotely, basically by telephone lines, kind of a very early version of internet-like connections today. And so that environment was actually very, very productive and a lot of fun. And I think that's actually the place where I first got seriously into computing, because I discovered it was great fun when you didn't have so many of these obstacles like punch cards and having to wait for jobs to go through operators and things like that.
And some time ago, you mentioned that if you're ever stranded on an island with only one programming language, you would have to be C. Can you tell us why?
I think, well, partly it's familiarity. I grew up with C because it was created by Dennis Ritchie, who was a colleague at Bell Labs. But I think in some sense, C is a fundamental tool. It doesn't rely on very much of anything else. It doesn't need a big runtime support from an environment. In fact, it doesn't need any at all. And it's a very simple, straightforward language. You could imagine building a compiler for it fairly easily for almost any target architecture that would be good enough. And so, in a sense, you can build anything else with C. In fact, if you look at the implementation of an awful lot of the tools that we use today, they're in some sense a shell around a bunch of libraries that are written in C, because C is both expressive, but also very, very efficient. And the efficiency mattered a tremendous amount. C was developed in roughly 1970, 72, let's say, so about 50 years ago. And at that point, computers were very, very much less powerful than they are today. They didn't run very fast, and they had very little memory. And so you had to make really effective use of all of the resources. And so C made it possible to do that. You could get very close to the computer. You could actually control what was going on in a way that is hard today with languages which are so much higher level and have so many layers of libraries between what you write as a programmer and what actually gets executed by the hardware. Yes, if I had only one language on a desert island, I would choose C, because with that, in principle, at least, I could build anything else.
You still remember the first time that you saw programming C and you tried yourself?
The evolution is a little different, I think. In the very early days, and again, this is the very early days of Unix, call it 1970, 71, something like that. First, people in the Multics project had been experimenting with writing all of the software for the system in a high-level language. They started out with a version of PL1, which was a very big, terrifyingly complicated language that IBM had developed. That didn't work very well, so they switched to a language called BCPL, which was done by Martin Richards at the University of Cambridge. And that was a lot better. It was a much simpler, more straightforward language. And so Ken Thompson, who had been involved in all of this, at some point created a even simpler version of BCPL, which he called B. And that language was superficially, it sort of looks like what C does today. And I programmed a bit in B, not a lot, but enough that I knew what was going on. And I wrote a tutorial document for B, sort of how to get started for the benefit of other people who hadn't yet learned it. And then Dennis Ritchie took B and basically added type information so that instead of the single data type that B provided, which is basically 16-bit integers, he converted it to a language which had data types like integers, perhaps of a couple of sizes, characters or 1 byte quantities, and eventually even floating point numbers. So, and he called that language C as a follow-on to B. And the difference between B and C was basically that idea now there were data types in the language. The language supported different kinds of data and did what was necessary to manipulate them as their own type. And I took the B tutorial, which I had written, and upgraded it to a C tutorial, again, so that partly to help myself learn the language, but also to help other people who hadn't encountered it yet and to get them off the ground. And so that transition is probably when I first started writing C, but I honestly don't remember at this point what my first C programs were or anything like that. I just have no memory of it.
Can you tell us a little bit of, you mentioned Dennis Ritchie. Can you tell us a little bit about your work with Dennis Ritchie and what led you guys writing the C language book together?
Yeah, so Dennis was a colleague in the same group as I was. He and I were both the same age. He had arrived at Bell Labs probably roughly while I was an intern there. He might have started his permanent job there roughly that period of 1968 or 1969. We were in the same group, and so I knew him through that. And I had, as I say, been writing these tutorials first for B and then the one for C. And C was becoming somewhat more popular. Certainly people who used it on Unix, which was at that time really the only place where you could use it, liked it. And so at some point, I suggested to Dennis that we should write a book about C. And I don't think he was originally very interested in it, but I twisted his arm and he said, okay, we'll do it. The reason I twisted his arm, well, a couple of reasons, I guess, but one is that he had written a reference manual for C. That is a very careful, precise description of the C programming language. And I wanted that reference manual as a part of a book. And the other thing is that he was just a great writer. He really, really had the ability to write clearly and concisely and accurately and with a certain amount of flair and even dry humor. So he was an absolutely wonderful person to co-write a book with. So he eventually agreed, and we wrote the C book. I wrote most of the first draft of most of the chapters. And the reference manual, I think we basically didn't change anything because it was so good. And then we made multiple passes over it to smooth out so it was a kind of a merger of our styles. And that was the C book. And of course, as a life-changing thing, that is by far the most important one that I ever did technically. The reason you and I are talking together is precisely because I worked with Dennis on that C book.
You're also the one who came up with the Unix term, right? So, and I was wondering if you could tell us a little bit about how did you come up with that term, and how was your work with Ken Thompson and others at that time?
Yeah, so the name Unix, my memory of this, and this is one of these things that is sort of lost in the midst of time. My memory is that the new system, this system, which today we know as Unix, had been written primarily by Ken Thompson at that point with some help from Dennis. I'm not sure exact timing. And people were standing around basically outside the offices. We were all on a long corridor and wondering about a name for this system. And I suggested that since they had all been working on this thing called multics, which was many of everything, you think back to the Latin roots of multi, many of everything. And this new system that Ken had created was at most one of anything. And so again, if you think of the Latin roots, uno. And so I suggested it be called Unix, as in UNICS. And somebody, and I have no idea who, made the great improvement of changing it to UNIX, and that name stuck. Is that the right story? That's what I remember, but I've told this enough times now that it it should be treated with suspicion. And there are certainly other people there who might also have contributed, in particular Peter Neumann, who was part of the original Unix group and was well known as a guy who just loved to create puns. And so Peter might well have done something like that as well. And I simply don't know at this point. I worked with Ken. I had nothing to do with the Unix operating system or the C programming language itself. I contributed documentation, obviously, like the book with Dennis, and a fair number of useful tools that go with Unix, but I had nothing to do with the system themselves. I think the only time that I ever really worked with Ken himself is that at some point, probably in the late 70s, I was very interested in document preparation systems. We had gotten a typesetter, that is a device for printing high quality stuff on paper. Think of it as an early precursor of laser printers today. And it came with terrible software. And so Ken created useful software for that. And I built on top of the software to make it a useful device for our basically internal printing. And so I worked with Ken on that, but that's other than that, and as a friend, but no actual technical work with him beyond that.
Must have been an incredible, absolutely incredible time. Brian, I was hoping you could tell us a little bit about the development of awk and also AMPL.
Sure. So awk it still is, a language that was meant to make it really easy to do simple text and numeric processing, the kind of thing where you want to stream a bunch of data past a process that does something to it, like identify interesting things or accumulate data or transform it along the way, sort of a stream processing kind of programming language. And it was created in 1977 by Al Aho and Peter Weinberger and I, and that explains the rather odd name. And we created it fairly quickly because we had really, really good tools available to us. It was written in C, of course. The grammar was specified in YAC, which was the compiler parser generator that Steve Johnson had created. the lexical analysis was done by Lex, which was an analogous program that Mike Lesk had created for basically tokenizing inputs very efficiently. And so we put all that stuff together. Peter did the first implementation, I think, literally over a weekend. And it's been used ever since. I mean, right now, if I were not talking to you, I would be working on the second edition of the awk book, which we wrote a long time ago, and trying to improve the code. So it's still very, very widely used, kind of a core Unix tool at this point. It's the precursor, in a way, of languages like Perl, and then less so, but in that same spirit, scripting languages like Python and JavaScript and so on. The idea that instead of compiling a language, you would interpret it, and therefore you could get off the ground more quickly. And also they were much more portable because you didn't have to generate code for each individual computer architecture. So that's awk, still very much alive and well. The other one you mentioned is AMPL, and AMPL is a language for specifying mathematical optimization problems. Things like linear programming is the most obvious example, where you have a system of equations that represent constraints on how much of things you need or have to have, or something like that, and an objective function that you want to optimize. So you use it for things like scheduling crews on airlines, or figuring out how to feed large numbers of people and give them enough calories, all kinds of things like that. Scheduling classrooms, packing things into boxes, all sorts of things are basically optimization problems. And all of them can be specified in a language that sort of looks like mathematics as you might write it on the board, but is more precise and processable by a computer. AMPL is that language. And an AMPL specification of a problem is converted into instructions for a solver, which knows how to solve things like, let's say, linear programming problems. The solver does its thing, finds a solution, sends that back to AMPL, and AMPL displays the results in the terms of the person who had the original problem. And so AMPL was, not the first such language, but I think has proven over the years to be by far the most successful of these. But it's a much more narrow area, more specialized than something like awk, but it's still very much around. There is a small company that I created with the two people who actually did more of the work on AMPL at the time, Bob Forer, who was a professor at Northwestern University, and Dave Gay, who was one of my colleagues at Bell Labs. So we created this in the mid-1980s, and I wrote the original version, and Dave Gay took it over somewhat after that and has maintained it since. And we created a small company in about 2000 to keep AMPL going, and that company is still alive and well, thriving at this point, although I don't have very much direct contact, or I'm not doing anything directly with the company per se at this point. But again, a specialized language is both awk and AMPL are, I guess, examples of what I might call little languages, languages that focus on a particular domain. Because of that, they can be smaller and simpler than general purpose languages like C or C++, things like that. They're also called domain-specific languages, I guess, if you're looking for a more familiar terminology.
And talking about other languages, you wrote a book about the Go programming language, I think with Alan Donovan. And do you think that you could take a Go to an island as well?
I probably wouldn't, for a couple of reasons. One, the book that I wrote with Alan Donovan, mostly is his work. He's just an amazing programmer, and he knows Go inside out like very few other people. And so I would, 90% of the work on the book was really Alan's, and I was not nearly as involved in that sense. Go is a nice language, and it does some things very nicely indeed. It's very good for network servers, crawlers, things like that, where you want to synchronize multiple processes very efficiently, very, very large numbers of things going on simultaneously. And it looks very much like C as well. It's sometimes been described as C for the 21st century. I think the reason you might not want to start with it on a desert island is that it actually needs some kind of runtime to manage the concurrency and garbage collection and other things like that go into running Go efficiently. So I would say it's perhaps not the right choice for the core stuff, but it would be perfectly fine as the next thing to try and do because it's very good at those kinds of concurrent operations that you might want. And it's also very much more a type-safe language. C gives you lots of ways to make mistakes, and I think it's so much harder to make mistakes in many of the newer languages, which are more strongly typed.
You mentioned a few times during the interview you have been around for a little while, and you have seen a lot in computer science and the evolution of computer science, and since the PDP 7 times. I'm just wondering, what do you think would be the next computer science related impact on people's lives? Something that you foresee happening in the near future?
Well, I hate to say it, but my ability to predict the future is pretty awful, roughly speaking. I mean, if I had been able to predict the future and, for example, use that to invest wisely, I would be able to buy a small country. And unfortunately, it hasn't worked out that way at all. So you should take anything I say about the future with a real grain of salt. I think that what we're going to see is that computing will continue to be just an absolutely central part of everything that we do. We've seen that in the last, call it 10 or 20 years, where more and more things are fundamentally devices that interact with the outside world, but are based on a computer inside, something that's running, an operating system like Linux and communicates with other computers by the internet. So the whole Internet of Things idea. And I think that's going to continue. That's one area. Another area that is clearly evolving very, very rapidly is all the things related to artificial intelligence and machine learning. I mean, the story of the week at this point is ChatGPT, which is something that carries on pretty sensible conversations or expansions of text in absolutely pretty much flawless text, flawless English versions I've seen that sound pretty sensible on an enormous variety of topics. And it will give you an essay for application to college, or will write a letter to a friend, or will generate a small program that is syntactically correct and stylistically good. All kinds of things like that. And that's very, very early days. I don't know how that will evolve. One thing that you see with that specific program is that it generates utterly nonsensical material that looks superficially perfect. And so you have to be very careful that what you get from one of these things is actually correct. So I don't know where, but I'm going to guess that in the next, call it 5 or 10 years, we're going to see a great deal more activity and probably progress in that ability of computers to do things like generate text, generate pictures, simulating the kinds of things that people do so that their behavior is more natural. And there will be good parts of that and bad parts of it. And the bad parts are going to be fundamentally, how do you detect things that are actually not right or are actively harmful in some way or another? Kind of deep fakes extended in many directions and very effectively.
And looking back through your incredible career, is there anything special that you think you have done in a different way besides perhaps forecasting the financial investments?
Yes, right. Yes, that's definitely one of the regrets of my life. Oh, well. No, I've been astonishingly lucky in a lot of ways because, as you go through life, you come to random events that send you in one direction or another, and there's no way to predict which direction, even if you realize it's a choice, there's perhaps no way to predict what the right direction will be. And so you just kind of do it. It's like rolling downhill and you run into a boulder and you go to the left of the boulder, the right of the boulder, and you just keep doing that. And so things that I have been very lucky on, for example, going to that particular program, that engineering physics program at the University of Toronto, where I was forced to actually learn a bunch of things. Going to Princeton for graduate school instead of staying in Canada, that might have changed my life. And in hindsight, it's worked out extremely well, but I don't know what would have happened if I'd stayed there or gone to a different school in the United States, which was also an option. And certainly that summer at MIT changed my life in a lot of ways, and then the subsequent time at Bell Labs. But it's very hard to see how any of those would have been different. Very hard to predict what the difference would be if I hadn't done that. So, for example, if I had had a different internship instead of the one at MIT, I suspect life would be very different. Would it have been worse? Maybe. Would have been better? Maybe. Who could tell? So I've tended not to second guess any of the decisions that I have made along the way. And one hopes to continue to be lucky in some way or another.
When you need to do some programming, do you still do C programming when you need to do something, or do you choose another language, or what do you do these days when you need to do a little bit of programming?
Most of the programming that I do is quite small at this point. It's sometimes writing code that will illustrate something for a class, or in this case, a book. And so it tends for things where I just want to get something done, and it usually is very small. I tend to write a lot of awk, which is self-serving in a way, but at least it's the language that at this point I know the best. I don't have to think about it in the slightest, but it doesn't scale to bigger programs. So if I write a 10-line awk program, that's probably getting too big. So after that, I would probably write Python, and I certainly use that for teaching. And I think that's, in many cases, for me, and certainly I think for a lot of people, the best choice. You get a lot of bang for the buck, and Python has an enormous collection of useful libraries. So there's a lot of code you don't have to write, you just use it. But for certain other kinds of things, I do write C. As I mentioned, have been working on the version of awk that Peter and Al and I wrote so long ago, upgrading it, for example, to let it process Unicode, which it didn't really do until I started working on that 6 months or so ago, so that it can handle languages of the world better than it did originally. And that's all C code. I hate to say it, it's not very clean C code. I wish I had understood good programming and abstraction and so on much better at the time when we were writing it, but it's actually kind of fun to do that. So those are the kind of the languages that I mostly use these days. If I were marooned on a desert island with something else, I would learn it fairly quickly, and that would be perfectly fine too.
Brian, like I mentioned to you, our programming group, the OsProgramadores, we have over 4,000 people who are trying to learn programming, trying to get into technology. And they come up with lots of questions, right? So there's, when you're young and full life, there's always a question if that's the right choice or the right decision. I'm just wondering, what kind of recommendations would you have for those that just starting the learning path?
I think probably the recommendation is to try as many things as you reasonably can. See what happens. For example, if you want a career in technology, see how far you can get with resources that are available. There's an awful lot on the web that you can use to teach yourself things, and groups that will help you along. Your podcasts are obviously an example of that. And so try things and see what kind of feels like you want to go further and what feels like that's not for me. And that gives you a better idea of what directions you might go. But it's a fine example of one of these random things where you don't actually know which is the right alternative, and the best you can do is try some of it and see what happens.
Just wondering, do you have any books, music, movies, or any recommendations, no matter what topic, that you'd like to share with the audience? I know you have a long list of books that I'm going to include in the podcast notes, but I'm just wondering if you have any specific recommendations, like, again, books, music, movies, or anything that you'd like to share.
There's a collection of things that I think people might find interesting. You may have noticed that Fred Brooks died within the last couple of weeks. Fred Brooks was the architect of the IBM 360, which is a computer system that set IBM on a path for many, many years. He was a very distinguished professor at the University of North Carolina. And he wrote a great book about his experience as the chief architect at IBM. It's called The Mythical Man Month, and it was originally written, I guess, probably in I'll make up a number, the 80s. I have to look it up. And then a new edition some years later. And it's a really, really good discussion of some of the things involved in doing software from the perspective of somebody who is managing a big software project. And it's really gracefully written in a lot of ways. And so that's one of a fairly small number of computer books that I go back and reread from time to time for whatever insights it might have. I mean, the world is different now than it was when Fred was working at IBM and then writing the book, but there's certainly good things in it. Another one that because it's sitting right close to me, I can see it, is a wonderful book called How to Lie with Statistics. And again, it's a book, it was written, I think, in 1953, so it's quite an old book. But it's basically about how to detect places where somebody is giving you the wrong impression with the numbers that they're presenting to you. It shows some examples of graphical trickery. It shows you examples of bad computation. And all of the text, in some sense, the numbers are a little dated because they're from the 1950s, but the ideas in it are timeless. And with computers, we can do a much more effective job of lying today than we used to be able to because we can draw even fancier graphics. And so I think it's a very useful small book that's kind of fun to read. There is, for people who are in English-speaking countries, a wonderful collection material on how to write English well, called The Elements of Style, which was written by Strunk and White. And again, it's a book that at this point must be close to 100 years old, but updated somewhat. And so I found that a book that is useful for helping me to write better English. And so for your friends and colleagues who are writing Portuguese, I'm sure there are similar books that tell you how to make effective use of your language to better communicate with the people who are going to read. And so I think it's one of those things where knowing how to write well is very effective. And knowing how to write well for people who are not as technically capable as you and I might be, write for audiences who are, their expertise is somewhere different. So how do you write a book for somebody who's, for example, a history major as opposed to a programmer, that kind of thing? And I think that's useful. I'm sure that you could definitely find examples of that sort of thing. Think about what makes good writing, what doesn't. And of course, along with that, a useful personal skill is how to speak well. Can you talk about what you do to an audience of people who are not in that field and make them think that's interesting? I learned something. And so being able to speak well about what you do is also a very useful kind of thing to do. And I don't have books on how to do that, but that's a useful way to think about what to do, how to make effective use of what you've got.
Those are fantastic recommendations. So thank you for that. And Brian, I realized I could spend 10 years with you, and we'd still have lots of topics to discuss. But I know you have limited time, and you so graciously volunteered that time here. I'm wondering if there are any questions that you believe I should have asked them today, and I have not asked it yet.
No, I think you've covered pretty much everything in a very orderly and organized kind of way, which is very nice and helpful from my perspective. So I really appreciate the chance to talk with you. Hope that some of this will be interesting for the folks who listen to the podcast eventually.
Oh, it's I can guarantee it's incredibly interesting. It's absolutely fantastic. Is there anything else in particular that you'd like to mention and share with the audience before we close?
No, I think that's probably the whole story.
And again, Brian, just want to take a moment again to thank you for so graciously donating your time. And I should let people know that we attempted this recording a couple of weeks ago, and we had a problem with the tool that we're using, and you agreed to record again. So thank you so much for your time. It's been an incredible privilege speaking with you today.
No, my pleasure. Thank you very much, Marcelo.
Cheers.
Chegamos ao final de mais um episódio. Agradeço a todos a atenção e o nosso site é OsProgramadores.com. Participem e até o próximo episódio. Um bom dia para todos.